Okay, so we're going to talk a little bit more about the quadratic formula and a certain part of the quadratic formula, which is inside the radical. It's called a discriminant. And inside the radical actually tells us a lot about what's going on graphically. So when using the quadratic formula, x equals minus b plus or minus square root b squared minus 4ac all over 2a, the expression b squared minus 4ac is called a discriminant, and it enables you to find how many real number solutions a quadratic equation has without solving the equation or graphing it. So, for instance, x squared minus 2x minus 3, if I wanted to find b squared minus 4ac, that would be negative 2 squared minus 4 times 1 times negative 3. So I get 4 plus 12, which equals 16. So we'll look at that for a second. The next one is b squared. So that would be negative 2 squared minus 4 times 1 times negative 1. So then we'll get 4 plus 4, which is 8. So the graph that corresponds with a positive b squared minus 4ac, it corresponds with how many roots or solutions it has. Notice that the graph to the right has one solution, two solutions. And that's because when we square root b squared minus 4ac, we get a plus and a minus that contributes to the quadratic formula, which is then generating the two answers. Next one, x squared minus 2x plus 1. So b squared minus 4ac would be negative 2 squared minus 4 times 1 times 1. So that is 4 minus 1, which is 0. So my discriminant is 0. A graph would look something like this, where it touches the x-axis just once. So it has only one real root, one solution. And why is that? Well, if you think about, again, the quadratic formula here, if you're adding or subtracting 0, you're not going to get two solutions out of that. You're only going to get one. Okay, next one. B squared, so negative 2 squared minus 4 times 1 times 3. So I get 4 minus 12, which gives me negative 8. So notice the graph that corresponds with that it doesn't actually touch anything on the x-axis. The reason why is when we put this in the quadratic formula and you have a negative inside a square root, you will not get any solutions out of that. So graphically, what that quadratic looks like is it's either above the x-axis opening up, or another thing it could be is it could be below the x-axis opening down. So for the following examples, calculate the discriminant and state the nature of the roots. So let's do it. So b squared, so 3 squared minus 4 times 1 times negative 7. So I get 9 plus 28 equals 37. So if b squared minus 4ac is greater than 0 and it is a non-perfect square, so 37, you cannot square root that and get a nice rational number. You'll get, 6 point blah, blah, blah. It's some kind of decimal of some sort. Then the equation has two real irrational roots or solutions, meaning you're going to get some decimal answers for this that are going on forever, irrational, right? Okay, so the problem with the next one is it's not written in ax squared plus bx plus c equals 0 form. So the first thing I need to do is move things over. So 3x squared plus 2x plus 1 equals 0. So that's the only way I can read my ABC correctly. So b squared would be 2 squared minus 4 times 3 times 1. So 4 minus 12 equals negative 8. Remember, we can't square root a negative number, so that corresponds with no real number roots. Now, this actually brings up a new topic. The square rooting of negative numbers brings us into another number system called the complex number system, and it takes into account what's called imaginary numbers. And if you're interested, Google imaginary numbers after you're done the video, and it's actually quite interesting. Unfortunately, we don't really do imaginary numbers until you take a linear algebra class in university. But it's not that it's hard, it's just that we have so many topics to cover in pre-cal that it's just one of those topics that don't get discussed. Anyways, let's do the next one. Now, I don't like fractions, so I'm going to multiply all of them by 4. So I get 4x squared minus 12x plus 9 equals 0. This way I don't have to worry about fractions. So that means I get negative 12 for the b squared minus 4 times a, which is 4, which is 9. So I get 144, subtract 16 times 9 is 54, so 9 and 5 is 144. So I get 0 out of this. And what does 0 mean? When I square root 0, I'm not going to get 2 solutions out of it. I will get 1 real number root. Again, it'll be a nice root as well. So it could be irrational or rational. So again, I can't do this unless I move the 4 over. So I have x squared minus 4 equals 0. Note that we are missing a bx, which means that b equals 0. So when I do b squared minus 4ac, it's going to be 0 squared minus 4 times 1 times negative 4. So I'm going to get 0 plus 16, which is 16. Now 16 is a perfect square. So if you get the discriminant to be greater than 0, positive, and it happens to be a perfect square, that is something kind of neat. Well, first off, if it's a perfect square and you square root it, you will get 2 rational roots, meaning you're not going to get crazy decimals out of this. As well, if it's a perfect square, that means that it could have been factored. So instead of using the quadratic formula, you probably should have used solving by factoring. So let's move on. Find the value of k so that the following equation has real and equal roots. So real and equal roots, that means they're the same, which means you only have 1. So the only way that happens is if you have it equal to 0. That means b squared minus 4ac equals 0. So b squared is k plus 6 squared minus 4 times 1 times 4. Where am I getting this from? Here's my a, here's my b, here's my c. I'm just plugging it into the discriminant formula. And remember, in order for you to have 1 root, that means it equals 0. So k plus 6 squared is a FOIL. So if I FOIL that out, I get k squared plus 12k plus 36, and then minus 16 equals 0. So I get k squared plus 12k plus 20 equals 0. And hopefully this factors. So if you go through the factors of 20, 1 and 20, 2 and 10, you can see that this factors to be k plus 10 times k plus 2 equals 0, which means k equals negative 10 and negative 2. So when k happens to be negative 10 and negative 2, then we will get 1 root. That's the same. So for what values of m will the following equation have real and unequal roots? So in order to have real and unequal roots, that means it's 2 roots. They're not the same, so you have 2 of them. So that is when b squared minus 4ac is greater than 0. So b squared is 8 squared minus 4 times 1 times, Notice that the constant here is a minus m, so that means it is a negative m that I'm putting it into. So this is greater than 0. So that means we get 64 plus 4m is greater than 0. I know it's been a while, but we learned how to solve this back in grade 9. So it's just like solving an equation. You just got to watch for, if you ever multiply or divide by a negative number, you got to switch the inequality sign. So if I move the 64 over, I get 4m is greater than negative 64. And I divide by 4. I'm not dividing by a negative number, I'm dividing by a positive 4. So I don't have to switch the inequality sign. So that would be negative 16. So when m is greater than negative 16, we will have real and unequal roots, meaning 2 roots. Next one. Given the following equation, for what values of k would the roots not be real? So if it's not real, that means they're imaginary. So that's when we have b squared minus 4ac is less than 0. Remember, they're negative. So let's solve the following. So that would be k squared or b squared minus 4 times 2 times 2, and that would be less than 0. So that is k squared minus 16 is less than 0. So now we got to think of how this is going to work here. Normally, if we solve it with an equal sign, we have to have, if I had, for instance, that k squared minus 16 equals 0, we could move the 16 over and we would get k equals plus or minus 4. So the problem is we don't know where it's actually less than 0. So if we do some testing, and actually in another unit coming up, we will be actually able to do this more algebraically than what I'm trying to show you right now. That's okay. So on this one, k squared minus 16, let's pick some points that are greater than 4. So, I don't know. I'm going to write this down. K is greater than 4. So let's pick a 5. If I put 5 in there, I get 25 minus 16. Is that less than 0? No. So that does not work. How about when k is between 4 and negative 4? So let's pick, say, I don't know, 0. 0 is between negative 4 and 4. Is 0 squared minus 16 less than 0? Yes, that works. Let's try when k is less than negative 4, because that's the only thing left that it could be. So again, if I plug in, say, negative 5 and I square it, I get positive 25 minus 16 is 9, and that is not less than 0. So this would be your answer. If you have a value of k between negative 4 and 4, you will get not real roots. Okay, so let's do the following. So it says, first off, solve by factoring. Now, anytime you have something like this where it's 6x squared minus 14x plus 8 equals 0, and you have an equation, you should use your Algebra 101 and do something to both sides to simplify things a little bit. And what is a common factor that we can divide out of both? A 2. So the first thing I'm going to do, no matter what method I'm going to use, I'm going to factor out a 2. So then I get 3x squared minus 7x plus 4 equals 0. So that should be always, no matter what method you're solving, try to solve it that way. So now we're going to solve this by factoring. So this is factoring. So we are going to try to factor 3x squared minus 7x plus 4. Well, there's only so many factors of 3x. It's 3x and x. So now we need to play around with 4. Our factors of 4 are either 1 and 4. And by the way, they both have to be negative because that's the only way I'll get a sum of a negative and a product positive. So 4 and 1. Can I play around with that? Would it work? Actually, 4 and 1 is going to work if I do it this way, because then I'll get negative 3x minus 4x, which will give me negative 7x. So set them equal to 0 and solve. So if I move the 4 over, divide by 3, I get 4 over 3. If I move the 1 over, I get positive 1. Does everybody see I get the solution for factoring pretty fast? Next one. I'm going to do the same thing, but this time I'm going to complete the square. Now you can see in a second this is going to get quite ugly. So 3x squared. So I'm going to factor out the 3. So I get x squared minus 7 over 3x. Leave a space, plus 4, leave a space, equals 0. So again, this is going to get ugly really fast. So why are we doing this? I'm just going to prove to you that in either answer we're going to get the same, or sorry, either method we're going to get the same. So if I take half of 7 over 3, I get 7 over 6. If I square that, I get 49 over 36. But really what I did is I added 49 over 36 times 3. So what is 3 times 49 over 36? If I cross cancel, I get 49 over 12. So that means I need to subtract 49 over 12. Now the problem is this 4 is not a denominator of 12. So that can be easily changed to be 4 is equal to 48 over 12. Right? Because 48 divided by 12 is 4. So what's 48 over 12 subtract 49 over 12? Well, that would be negative 1 over 12 equals 0. So now I still have to solve. So I got to move the 1/12 over. So I'm just going to get this out of the way. So 3 bracket x minus 7 over 6 squared equals 1 over 12. I'm going to divide the 3 over. So if I divide by 3, that's the same thing as multiplying by 1/3. So I get x minus 7 over 6 squared equals 1 over 36. I'm going to square root. So I get x equals plus or minus the square root of 1 over 36. And somewhere we should have learned that we can square root the top and the bottom separately. And we get, sorry, I missed my x minus 7. X minus 7 over 6 equals that. So x minus 7 over 6 equals plus or minus 1 over 6, because the square root of 1 is 1, the square root of 36 is 6. I'm going to move the 7 6 over, so x equals positive 7 over 6 plus or minus 1 6. But we need to get two solutions out of that. So what's 7 over 6 plus 1 over 6? 8 over 6, which is 4/3. What's 7 over 6 subtract 1 over 6? 6 over 6, which is 1. Hey, look at these solutions. They're the same as that one over there. Was that supposed to happen? So now let's do the quadratic formula. Quadratic formula says x equals minus b, so 7 plus or minus b squared. Minus 7 squared is positive 49. Minus 4 times 3, which is 12, times 8. Sorry, times 4. I'll say that again. Minus 4 times 3 times 4. So 4 times 3 is 12. 12 times 4 is 48. So I'm going to be minusing 48 all over 2a, which would be 6. So x equals 7 plus or minus the square root of 1 over 6, which is, what's the square root of 1? 1. So 7 plus or minus 1 over 6. So again, what's 7 plus 1? 8 over 6, which gives me 4/3. What's 7 minus 1? 6 over 6, which gives me 1. Hey, I got the same solution again. You should. We're solving for the same x each time. We should get the same solution. But I want you to notice that if I gave you, say on a test, solve the following quadratic, and you were having trouble factoring, you could try to go into the, because you can notice that the quadratic formula was way easier than completing the square, which of course factoring was the easiest out of all three. So your first method should always be trying to factor. Your second method should always be going to the discriminant. But before you do the quadratic formula, before you do the quadratic formula, try the discriminant. If the discriminant is a perfect square, that means that the quadratic equation is factorable. So, and if it's not a perfect square, then you've done half of the quadratic formula and keep going.